Yeah, my name is David Otten. I work with C&W Services. My background, I'll go over in a minute, and this is Abhinav. He and I have worked together, almost 18 months or so on different projects. And so the goal today was just to show you one example of one project we worked on and help you understand if you're evaluating wireless vibration sensors and those kind of things, where it might come into play for you. So first off, I've worked several different places. The majority of my work has been with GE Healthcare, and I started September 21st, 1986 as a field engineer in North Carolina, and it's led me all the way up through to Milwaukee, where I worked at GE headquarters for a while. And since then, doing a lot of facilities maintenance. I'm now working with Cushman Wakefield. Been with them a little over a year and a half, and several different projects. We have several clients in the U.S. We're number 3 globally for commercial real estate and hard services. And we also provide soft services, which is janitorial, landscaping, that kind of stuff as well. Majority of our work is in the U.S. We do have sites in Canada and Mexico as well. I've done a lot of work in pharmaceutical and some production manufacturing and critical work environments for our organization. And the core competency of us, obviously, in C&W Services is the hard services. So I work with a lot of mechanical engineers, electrical engineers, operations managers, those kinds of guys in different groups and different environments. So I get to see a broad spectrum all the way from critical work environments where you have lots of redundancy and lots of reliability focused attention, all the way to office buildings and those kinds of things. So I get to see a good disparity. We do have one project that we worked on out on the West Coast, a 173-acre campus, had over 40 buildings, 350 critical assets, and what we mean by that were these were significant enough for the operations to have full-time reliability guys going out and doing hand-based monitoring. So they had their fluke meters and different things and going out every month, checking the condition of the equipment, several thousand pieces of total assets, but 350 or so critical ones. And some of the things to be aware of in a pharmaceutical industry, you do have live animal research, you do have lots of viruses and other things that you're testing. So all of the research labs had exhaust hoods that ran 100% exhaust. So if you can imagine 150 cubic feet per minute times 1,000 in a large scale building, the volume of air that you have to condition coming into the building, plus the volume of work that has to go into increasing the capacity of the system. So one large building may have 4 or more 100 horsepower plus air handling units just trying to supply that volume of air. And so a lot of the challenges we had, it was on a network. So across the campus we had chilled water and steam network as well as compressed air network. And so you'd have 3 or 4 main boilers or chillers in your utility plant, but through the other buildings you'd have satellite steam generators and satellite chillers. So you had to monitor that as well as far as balancing. So if you ever set your controls up wrong, as you're aware with a chiller, and you kick it on for 30, 40 seconds or a minute or 2 and then shut it off, do that 2 or 3 times and it's not going to start anymore. You really have to run them at 70, 80% versus 100% and 0% kind of scenarios. So being able to balance that and monitor that was quite a challenge for us. And some of the concerns we had were, how do you keep track of the condition of that stuff? So having my Six Sigma background, trying to think statistically about this, I looked at the way we were doing the condition monitoring of our critical assets. And you all are familiar with this curve, right? So when can you actually detect vibration? You can detect it about right here. Most studies show that with a bearing under load, typical scenario is 9 days or less before that bearing actually destroys the shaft it's on and everything else once you start seeing significant vibration. Well, if you're doing once a month testing, you're testing it, day 0 through day 21 before you actually catch it. So 70% of the time you're not going to measure it whenever it's in a failure condition if you're only doing it once a month. And so for our 350 units, we had 2 full-time guys going around getting once a month samples, and there's no way that I'm going to be able to add 6 more guys so I can get weekly samples. And even at weekly samples, you still have, what, 2/9 or 20% of the time you're going to be measuring it before it actually starts its failure, and by the time you get back to it again, it's past the point of no return, as it were. So that's the reason we were looking at, we have to do more frequent sampling if we're going to catch these things in an early fault condition. And so we were looking at what are the solutions that are possible for that. Many of our systems were closed systems, so we had sensors hooked to them with the BNC connector so you could go by and do it faster. But still, you got one guy going and doing this one, going and doing that one, and a large campus, 40 buildings, he spends half of his time going back and forth between buildings. So the goal was to come up with a solution that would give us enough data collection and so that it would be beneficial to us. And so that's why we were looking at what can we do. And that would be my statement to everybody. The value of your technicians, you know, skilled guys that can do vibration analysis should be troubleshooting your systems that are struggling. And if you're consuming their time doing rounds and readings that you can actually use technology to solve, then I would suggest moving to technology to try to do a lot of that monitoring and get your resources on your repairs and significant troubleshooting. So that's what we were looking at. And so here's an example of the air handlers, right? So they're in a closed case, and so we wanted to at least set up a trial. Will this work? So we identified 6 or 8 systems. So out of the 4 air handlers in one building, we put the monitoring on 2 of them. We put the monitoring on an air compressor system and on a chiller and on a circulation pump. Just to, you know, we really wanted to see how this works. And so the focus was we didn't have a lot of money, but we had enough that we could, you know, spend $18,000, $20,000 and get that up and running. And we wanted to get as much higher sampler rate. And of course, the new wireless systems, here's the one that like we actually used. And you can set those up to take samples at whatever frequency you want, you know, once an hour, once every 3 hours, once every 6 hours. And as long as you're doing once every day or so, it's much better than what we had, right? And so depending on how long you want the battery life, how much attention you want to pay to the particular equipment, and the advantage, of course, is then you can also increase that. If you're sampling once a day and you're starting to get concerns, or you're trying to do load monitoring, you can set it up to be more frequent. And so our goal was to get something with enough sample rate that we weren't missing bearings and stuff after they started failing, and something simple enough that we could install it. We only had 2 guys that could really read wireless or vibration stuff. So our guys that were working 3rd shift on Saturday in the controls room, we didn't want them trying to diagnose and analyze this kind of stuff. So we had to have something that was simple enough that it would at least alarm, and they would say, oh, this is an alarm. What kind of an alarm is it? I guess I better triage this and call my wireless expert guy to look at it. So focus trial, and it was a very simple setup. There's 4 basic pieces to this. One is you have to collect the physical information, right? So you have to have a sensor. You have to somehow get that information up so that you can use it. These and almost all the others over there will use basic technology. You can either have a proprietary network or use an open architecture network. We use the 802.3 IP stuff on these. The Wi-Fi was already prevalent at the site. We talked with the IT group to say, hey, we think this is a real value add for the reliability of the system. One of the challenges you always have, and I think I heard it yesterday in an implementation, involve your IT group early, especially when you're trying to use the networking of your facility. And it only makes sense, right? The guy ahead of your IT department is his CIO, right? He's the Chief Information Officer. He's the Chief Innovation Officer in a lot of cases, right? And so if they're helping you solve this, you can probably get a much better implementation, much better coverage. If you can't get network coverage because it's in a mechanical room, they'll help you add and expand to that. So have them on your team to help you to solve this. You can easily make the business case that it's bringing value to the organization. It's helping them expand the information capability and the innovation at the facility. So you guys have a mutual interest in working with them to try to get that done. The next piece was we wanted some, wrong way. We wanted to, wrong way, where's it going? We wanted to get some cloud-based learning right here, and that's because we don't have that many wireless experts, right? And I think that's the biggest challenge. I was talking with Abhinav earlier, that the biggest challenge we have right now is not the technology, because I can walk over to the exhibit booth and probably half of the vendors there have some wireless monitoring capability, and you can put it in and get it working. The challenge is, okay, now I'm getting the signal. What am I going to do with the data that I'm getting? Well, I need somebody smart enough to read it. And so it's kind of a science, right? It's a magic, because it just happens and we don't understand it until we understand it better. Then it becomes a science. So you have really smart people who can understand it, and that's kind of where vibration monitoring is at right now. If you have people trained and are pretty smart, they can read the data and tell you what's going on. And eventually you want to get to make it simple enough that the average user can have benefit from it. And that's where machine learning really comes in, is you want to be able to I guess, turn it into a very monitoring-based, binary-based scenario where I just need to understand when my equipment's in trouble and I need to triage some support to it. So the majority of my support staff can then manage it. And then the other piece, it would be, can I get to this with my common technology? I think the holy grail we're trying to get to is one screen, right, for our building automation systems, our control engineers, our fault diagnostic systems, and this just becomes another attribute to that, right? My air handling is low. Why? Well, my BAS alarm is showing this, my airflow meters are showing this, and oh, wait a minute, now I'm looking at my actual air handling unit, and there's a large vibration and the temperature's going up on the main bearing or something. Then you kind of know what's going on, right? And so it really adds to that. And so if I could say anything, it's not a complex implementation. They're all very similar. And you can definitely do a trial on a small scale at your facility without a lot of effort. And so I don't know why. That was not supposed to do that. I apologize, I'll have to go back and fix this. I did not push that button, by the way. I only wanted to advance the screen. I should go. So I'll walk through it. And so we did start a trial. The advantage of the new technologies, they're really easy to implement. If you involve people early on who are going to help you with the IT group and others. We ran our trial for 9 months, and because we were able to use the existing network within the facility, that significantly reduced our cost, as well as simplified the ability to get it loaded onto the cloud and then bring the information back in for monitoring, right? And again, we selected some specific equipment because we wanted to do side by side. One building had 4 air handlers. We put monitoring on 2 and not on 2. And we just wanted to do side by sides. And of course our goal was prove that it works. And so we wanted to be able to get data collection at a sample rate to say, well, we can catch it before a bearing's failing. We wanted to, one of the things we learned is this ability to correlate this to the operational data. And we'll show you an example here in a minute about, you can actually, if you have your sample rate set up, you can tell when your equipment's even on and off, right? So when you're getting into energy management, you can see if they're running on the weekends and that kind of stuff. And the key piece is, I'm in Milwaukee, right? And so this is out on the West Coast. And so when we start getting alarms or looking at data, I'm not going to get on a plane and fly out there. So the advantage now is with virtual, right? Once you get it up in the cloud or you get it into a network-based system, you can access it anywhere. And not only does that help me, that I get a call that something's going on, but I can call Abhinav or one of our vibration experts and say, hey, come look at this. And of course, the advantage there is I could have multiple facilities now, and I could still get to one single pane of glass, at least for my vibration monitoring. And I could have 1 or 2 experts on my staff of 50 or 100, and they would still be able to monitor a large number. So again, 350 units, we have 2 full-time guys just taking samples once a month. I could easily have 1 vibration guy monitoring that many or more. And do other things because it'll alarm and tell him. They then manage by exception versus trying to take a sample of everything. So very advantageous for us there. And of course the goal there was to prove the value. So my challenge to Abhinav was, okay, show me that this is valuable. I knew it was valuable to me because I could recover my resources times to do other things, and I could catch these things before they failed. But I challenged Abhinav. I said, okay, so show me a couple of values, right? And I didn't tell him that I had already justified it, but I wanted him to prove it separately. So, so then my challenge was, okay, show me that this is going to work.
So yes, absolutely. There are some immediate benefits when you go live with a wireless system. You don't have to go collect data regularly. Folks are strewn all across the world, all across the country. You can get you can get the best analyst. You could get an analyst that's not in town. And in businesses like C&W Services, they have many clients. You need to scale your vibration analyst, right? So that's kind of what a wireless system helps you do. But all of that is, bells and whistles, in my opinion. Really the heart of any system, be it wireless, be it wired, be it data collection, whatever it is, what you really need is to catch a defect. And so we had 2 aha moments that we proved. I mean, he challenged us, show us where's the value in this, right? And I think, as a up and coming startup, we're really hungry to, prove that value. And if it's not valuable to you, we don't want to be in business. We don't want to waste our time and your time, right? And so that was very important for us. And so here was a scenario. We were monitoring, a particular air handler. They have some huge ass air handlers, and they're very complicated to go and get data, lock out, tag out. If you guys are familiar with that, turn it off, get in, put the sensor, come back out, turn it on, take a reading. By the time, many things can happen, right? And so the first aha moment was actually a anti-defect. Have you heard of an anti-defect? I'm going to show you one today. It's not a defect. It's actually, look at this data here. These are vibration. If a vibration guy, data collector guy, went out there and collected the data, they would show, oh, the vibrations are increasing. This is overall RMS, overall vibration levels. Overall vibration levels, as the experts may know in this room, are not the best indicators, but are a good starting point, right? They're not sufficient, but they're a good starting point. Now, if you saw a reading like this, if the data collection showed that, hey, the vibration is inching upwards, let's go create a work order, let's go fix it, let's be all on it, and let's start fixing a problem, because there is a problem, right? Guess what, is there a problem? Actually, there was no problem, because the data is all over the place. The vibration data is up and down and up and down and up and down. So now, this wireless real-time data is giving you a lot more data, and if a walk-around guy went around and collected data, they would be collecting it on those different points, and they might think that the vibration is gradually increasing. It's not, right? It's actually going up and down and up and down. And here's a quiz question. Is it random data, what you're seeing here? Can anybody guess what's the pattern here? This is an air handler that we were monitoring for a C&W Services client. And, I'll give you a hint here. Look at the peaks. How many peaks in each set? You're getting there? Exactly, yeah. So those are the different days of the week, Monday through Friday. Daytime is up, evening is down, weekends are down. Why? Because the scientists are working, daytime, normal business hours. The air handlers are, running full steam, because otherwise their labs, they have set requirements for providing the right HVAC conditions. That's how, so what's happened in this case is operations data is now readily available to you on, a predictive maintenance system. And why is that valuable? Because 101 of vibration science, right? You can take vibration readings, but if you take it in situation 1, the load is very different from situation 2, as it was the case in the blue line. You will have the wrong results. You need to have this apples to apples comparison, right? And so if you're comparing the vibration trending, you would rather compare it around between a point here and a point here, or maybe a point right there and a point right there, because you need to be apples to apples. The load has to be similar, right? And that's kind of what real-time data helps you with. And so what we did was we helped them. That's why it's an anti-defect. It was not a defect, which they thought could have been a defect. And we save them all the repair dollars and creating a work order and all the headache and the hassle that comes with that. So that was one use case, and clearly that helped them. Here's another one. So that was Monday to Friday, as the lady pointed out. Here's another aha moment. This time it was a defect. This is an air handler. You see this is a 100 horsepower motor probably, and there are about a dozen of these air handlers, which they kick in and kick out. Like they have a schedule that the predictive maintenance guys don't know, because that's in the realm of the operations guy. The BAS guy, they stay on top of that. It's not the job of the predictive guys to know it, or they don't have access to that information. They probably don't know how to see the BAS system, what parameters to look at. And so that made the predictive maintenance job hard, right? So in this case, you have an air handler, they are resting, this fan is resting on a two pillow block bearings on the two ends, and that's the wireless sensor that is here. It's called the PetaSense mode. And the monitoring had begun about in March time frame, and the overall vibration started to inch upwards around here. And obviously, that's the first, if it's a source of concern when you have the overall vibration go up. And so, and you had the real-time data, so in this case, you knew that it was not just an operational thing like the other example we saw previously. And it went up, so the data was in Silicon Valley area. The customer was in the San Francisco Bay Area. And they needed an analyst. The analyst was sitting in Southern California, so they called them and we asked them to, so we asked them to look at the data, and they looked at the data and they assessed it's a misalignment and increasing bearing clearance, and not by looking at the overall RMS, you cannot do that, right? So they looked at the spectrum, which is also available on the software, and many softwares provide that, but things are moving more and more to a web-based, online, anywhere access option. So in this case, the analyst was able to look at this data, the spectrum data of that particular point. In this case, you can see a clear, an increasing noise floor, and you could see the spectrum for any of these points. Each point can give you a snapshot like that. So you can have a waterfall model you can look at. And then also the low frequency here has a bunch of peaks. And if you zoom into that, you look at the peaks are actually the bands are mapped to the blades of the fan. Okay, and so clearly there was a defect, so a work order was put in, AHU shut down for repairs, and another AHU was kicked in for the operations, and then when it came back, you're back to kind of a steady overall RMS. So very normal kind of a defect situation where you saw something went up, you could take action, but what was new and what was different is, data was real time. You could see the spectrum anytime. You got an alarm on your phone. The analyst was sitting somewhere far away, not in the same office, and you could take action and prevent unplanned downtime. Everybody talks about unplanned downtime. This was a case in point. That was an aha moment. So those were the two aha moments which really, we took the challenge and we proved it to Dave and his team that, hey, look, this is the advantage of going away from manual data collection and be able to, and you can still do your manual data collection, but do it on a prioritized manner. You got all this data coming in from, oh, go back a little bit here.
Well,
I'll go back to the pillow block here, yeah.
Well, I just wanted to point out, if you've ever worked the pillow block, if you've ever had one of those fail and you didn't change it in time, and it heats this shaft up so that you see the little rings around it and the shaft warps, that's very expensive to replace.
And you did have a case before we showed up, right?
Yeah, that was one of the reasons we moved with this, is we'd had a couple of scenarios of failures like that, even though the guys were lubricating them with the correct frequency. We had one where they did the sampling and they caught it early on, but the other one where it failed, and by the time it failed and we were able to detect it, because again, that's in a sealed chamber, right? And you have to do lockout tagout to go in there. And so by the time we found it, we had to replace the shaft and the pillow block, and that cost more than our entire pilot to do that one. Yeah.
So hand it back to any
questions?
questions?
A question.
And how long was that failure regression?
Well, it was like 8 or 9 days.
The previous one, I think, talk about the old one.
So looking at only at overall to attract your attention to this?
Well, again, that was part of the thing. When I was brought in, part of it was to drive reliability, and I'd seen a couple of those failures, and I said, and that's what drove me into how are you actually doing the monitoring? And it was they do the monthly PMs and they do the monthly vibration checks. That's all they were doing.
But they're only looking at overall?
No, they were looking more than that as well, but still.
Because a normal bearing failure for something like that, you could have 2 years to see it coming.
Really?
Right.
And yeah, if you're looking out there between 20 and 65 orders, you're going to see that thing coming miles off.
Okay.
Not 9 days. That's why I'm trying to figure this out.
Okay. All I knew was it was failing, and my samples weren't enough to catch it. And analysis on bearings are typically under load. They don't last that long. I mean, so.
Yeah, again, you're looking only at overall. you're gonna miss it.
You're gonna miss
Okay,
it,
You're gonna
exactly.
fair enough.
That's my big problem with this. Is
That's important.
looking at
Fair enough.
overall.
Yeah, that's why this is not overall. That's why if you see what was done here was to look at the spectrum. You cannot just look at the overall. What's that? No, the alarms they even set on the bearing. This is just to demonstrate here easily that overall is a good way to see the trending. But in this particular case, there was also an alarm since we had set the alarm date.
It was more the example of the earlier one of a once-a-month sample where you take a sample and you send it to somebody to look at that 5-second sample or whatever,
Yeah, I
once a
understand.
month
It's just
versus.
that Overall, you're gonna miss bearings all the time.
You should
in
never
general.
look at just the
That's all.
overall alarm.
And that was kind of
Absolutely.
my premise, is that you should be doing condition monitoring, not
Exactly.
once-a-month sampling if you're not doing the right analysis, right? So, yeah.
Let's go back to what you got out of that, yeah.
Yep, this is a high-level overview, not counting the false alarm, which wasn't an alarm, it was just the sampling scenario that he had shown as a value. There were 2 defects that we did catch, one when we first started the trial, and then another one on, which was really our cost justification for could we justify the cost we spent on the pilot, were we catching stuff before it got into a degraded state? And it definitely proved that a couple of times over. And as soon as we got additional funding, then we scaled it up to, now we're doing a little over 40 machines. And as funding becomes available, we want to eventually do all 350. And again, the advantage of these are, especially if you're running in an open network, is you can put 4 or so on a significant piece of equipment to make sure it's well managed, and then you can actually move them around to other systems as well, so you can have some flexibility there. And so that was the key thing, is we were able to cost justify it as well as prove that it was definitely worth the effort. So wireless is not perfect, right? But it's certainly better than pulling wires everywhere. I was in the 1990s, I was doing field service for a medical company, and we were installing all the patient monitoring, and it was when internet capability and central station monitoring and all were moving to the internet age. And I went to Roanoke, Virginia, and I spent 3 months pulling RG58 and Cat5 cable through every hole, every wall, to every patient bedroom, and in the whole place. And it was, I forget how many, 300 and some beds of monitoring that I had to pull all this for. But with wireless, you literally just, if you got wireless access, it's so much easier to install now. Well, it's because, the biggest example is most air handlers are in a metal box, right? And you put these sensors in there, unless you have a good signal in the area, you're not going to get a signal out. The second one is everyone's very concerned about security. So if you just walk in and start putting IT devices or internet-enabled devices in a facility, your IT team's going to come and start asking you some very direct questions, right? So you have to involve them early to make sure you're managing the security piece. You also have to leverage to make sure you have enough coverage, right? Now, if you have cooling towers and stuff out in the middle of an area where there is no support, you can do the cellular. Verizon has a little box and those kind of things where you can do hotspots and those kind of things, and that works well, right? And I know that several of the scenarios have been locomotives and trucks, and lots of mobile equipment now have the capacity, and the fact that it's standardized really helps. So the other part being it's battery powered, right? So if you're trying to do continuous monitoring or samples every 2 minutes, you're going to burn the batteries out quick as well. Yeah.
We have tens of customers who are running, monitoring their critical, semi-critical machinery with these sensors. And the first problem we have to figure out is, there is no network in many of these plant sites. Everybody's in their office rooms has Wi-Fi, but not necessarily in their machine areas, in their plant area. And so it's a good problem because you're now bringing connectivity to these areas, but it's a problem that you have to take on sometimes with it. In this case, we were extremely fortunate. They already had a Wi-Fi network, and it was in the building premises. These machinery were kind of in the basements and all that, and the Wi-Fi was, whoever did Wi-Fi, they did it well, so they had coverage in every area already. But otherwise, it's not perfect in the beginning. And the other points that you mentioned are pretty valid: security and, getting access in every corner. Those are the kind of things to think about. Back to you.
Yeah, so, I'm sorry, go ahead.
So on that So this was not on dedicated Wi-Fi, it was done on the plant network. And how did they deal with that from a security standpoint? I'm sure they were concerned about, bringing this onto the plant network.
Yeah, we talked with the IT group early on, and again, this was one-way communication. These would only transmit data up, and so you couldn't go back and talk to them. And then once we got it into the IT campus network, they had firewalls on what they could allow, and so they did some gating and those kind of things to allow these to transmit past the firewall outside to the cloud, right?
There was another reason why IT was completely on board with this is because this is not connecting to your building automation system. This got a complete air gap, so it's just, it cannot turn things on or off. So imagine we hear about stories of, a malicious virus took over the Jeep, because the software, the embedded software of the car got some virus. This cannot, because it's an air gap. And so that's something to consider when you're looking at solutions. Is it getting on my network, like my control systems network, turning things on and off, or is it an air gap, it's over the top? And that's one of the reasons by design we chose not to integrate it with the BAS from the network. If you want it on the BAS, like they want it on Pi, they want it on the historian, we take it up to our cloud, and then from there you can securely send it to a historian. But just because you need the data to be in a single source, don't let the sensor come into that network. So that way you have a clear air gap. So that's how it was addressed.
For the air handling units, how many points of contact did you measure as part of your pilot?
We measured 4. We measured the 2 ends of the motor, and it was belt driven, and we measured the 2 ends of the shaft.
How often did you collect the data?
Sampled every 3 hours.
Sample every 3 hours.
Yeah.
And in terms of the analytics of this data, it goes to the cloud, and there is a scientist analyzing and providing some feedback, or the application solution that you provide already do that?
Yeah, so again, we were looking at something that would take some of the science out of it and the magic out of it. So our goal was, if there's a problem with it, flag it and have the technicians go and do a top to bottom assessment, right? So you can get complicated enough to say, I need to know if it's a coupler versus a bearing versus a whatever. But if my years of experience have been, I'm never going to go, especially in a van, and travel 2 hours to a site and only take part of the parts, hoping I guessed right. I always assume it could be a lot of things. And so my premise there is, if the unit is in distress, I should have somebody who's knowledgeable of that unit do an overall assessment and find out what's really going on anyway by the time you need a service call. The advantage of the cloud and the virtual piece is, if I'm seeing some hokey stuff and I can't find anything wrong with it, they can at least help me further analyze it and say, well, those are the harmonics of the fan. You might have a fan out of balance, or those kind of things, and that really helped as well.
The other part of your thing, that was the right point here. In terms of the machine learning part, right? The data science doesn't look at the data every single time the data comes in, or not even when they're invoked. The data scientist has built a model based on the asset classes, fans, compressors, air handlers, and so on, and understanding their failure modes, understanding, where are the sensors placed, what are the machine information, the running speeds, and whether it's a VFD, non-VFD, and all that. And that model is what creates a health score. We didn't get into our product because we're not trying to sell, we're trying to explain the C&W Services thing. But typically other systems too will provide some kind of inferred value, because the vibration has many parameters. This little sensor gives you 40 tags, right? And if you have 4 of these, you got 160 tags coming in. So you cannot manually look at every single one of them. So the machine learning model kind of watches all of them together all the time in real time, and then flags an issue, and then you can pull in an analyst to say, hey, look at the problem machines. So if you've got 150 machines you're monitoring, and each of them is spewing 40 tags, you cannot scale that program if you're manually analyzing all of that. So you don't need just wireless data. It's impossible to manually analyze all of that. So you need one level of software, and then it becomes the assistant to the analyst. That's how we think about it. Sorry.
Can you define what a tag is?
Oh, a tag, so this is a triaxial sensor, and it also has a temperature sensor. So a tag is each vibration, when it takes data in the x-axis, it is giving you the raw vibration data. It's a waveform data, okay? I don't have a picture here. And that waveform data can then be converted to a spectrum, okay? Now, from the waveform, you can compute the average vibration, you can compute the peak to peak, all of that is a tag, right? Because you collect a waveform every 3 hours, it gives you an average RMS. So now you have 8 RMSs per day, right? Because you're doing every 3 hours. So so you get a trend of the RMS, you get a trend of the peak, you get the trend of the crest factor. So those are broadband tags, the waveform tags. Then you have the spectrum. On the spectrum, you have those peaks, the forcing frequencies, the 1x's, the 2x's, the bearing tones. Each of those can also be trended, and those become tags. So the tags are all the machine parameters, the forcing frequency, the broadband parameters, and that's why those 4 vibration x, y, z are then, you derive from that all these other 40 parameters. Does that make sense?
Do you have band alarms that you can
Oh
put
yes,
on these?
we do band alarms, overall alarms, and envelope alarms. So 3 kinds of alarms you can do. You can do the overall on the RMS or the peak on broadband features, or you could do band alarms. You could do it on your 1x to create a range and set the band alarm.
Yeah, how many envelopes can you put on one of those?
Well, you can put as many because it's just software, so you can add as many bands as you want if you're talking about bands. As far as the envelope goes, you can take one spectrum, and then you can say one standard deviation from the spectrum. If you have a problem, raise an alarm, or 2 standard deviations is a critical alarm.
Right, but you can create an envelope between 21 and 65 orders.
Say one more time, I couldn't hear you.
We can create an envelope between 21 and 65 times turning speed.
Yeah, you could do that. And
create band alarms
yeah,
there.
in our software we call that band alarm. But in our software, envelope alarm is all the way from 0 to the F max of this guy, and you set a whole envelope. But I think you could, if you set it to a smaller range, that would be a band alarm because it's a small band.
Right. Okay, thank you.
Okay, good question, by the way. Thank you. You have a question there. He's been waiting for a while.
Not
over there.
working. Okay. So before you made that decision to go wireless, did you do a comparison between the wired system versus wireless? And if you did, how much cost difference was?
Yeah, we looked at, can we get samples frequently that we need, and how easy is it to install? And the challenge with wireless now, with wired is now you have to actually get a physical Cat5 cable or something to the box. And in the example of where you saw the pillow block bearing, you literally just walk up with your epoxy and stick them on where you need them, and then you can set and program them and get it working. So it's so much easier with wireless. It's, it's like your Alexa and your smart TV and everything now. You don't have to pull wires through your walls, right?
And the biggest cost differential is the cabling, because we are coming up with a new product. We don't have cable. 5 minutes. We don't have a ton of cables in it. It has just a short sensor cable, but the cabling can be time consuming, and time is money because labor is the biggest cost in all of these projects. Okay. The other question, the gentleman's waiting for a long time, so I'll let you ask.
The first AHA non-event, would the AI eventually rule that out, or do you have to go in and manipulate this so you don't get false alarms all the time?
Right, at the time when that was caught, it was last year, and it wasn't AI, it was manually we looked at it because we were kind of doing the extra work for them. So can AI catch that? Eventually, but I think that's why I said I know enough data science to very happily say that data science cannot take over some of these complex things. What it can do is be a good assistant. It can do repetitive tasks well. It can't do subjectivity tasks well. So that requires some level of subjectivity. So what could have been done in that scenario is, in the data science model, now we are trying to ignore the floor and just take the daytime values, right? So you can model it. But at that time, it wasn't data science in a nutshell.
But that's a very good question, right?
Yeah.
Is how do I plug this in and know it's working? And every scenario, and we've tested others as well, is there's this burn-in period, learning curve, and all this other stuff of what's the good behavior of my equipment. And I think you almost need to be pretty confident of the condition of your equipment when you put the sensors on them, or else, if it's a high threshold, you think my equipment's already in bad shape, or if it's a low threshold and it maybe it's not supposed to be, kind of a thing, right? So have some knowledge of your equipment.
And multi-parametric.
And that's easier, right, to do like an initial burn-in test, right? There's some standards in the wireless vibration, or excuse me, in the vibration testing scenario of if it's more than 0.5, it's probably the bearing is showing some significant degradation, those kind of things. But understanding your equipment is good, and we did, over the course of the pilot, adjust some of those alarm limits. Some of them it was way below, so we pulled them a little tighter. Some of them it was really close, and we were getting an alarm once a week, and we would go check it, and it's fine, and so we raised them up a little bit because we were comfortable that it was oversensitive, right? So.
But multi-parameter, I just want to add one point on that, right? So what we got from that, we actually took it into our next product, which we're about to launch. I won't talk about the product, but what I'll talk about the concept. You know, when you look at a rotating machine, load is important, running speed is important. So if you just look at the overalls, you're going to get garbage. If you're just going to look at the same 1x in your spectrum, you'll get garbage. You need to look at in comparison with your other parameters. What's your load? What's your running speed? And so you need to have other sensor inputs coming in. So how do you measure load? In the case of an air handler, you could use, you know, there are some pressure sensors you could use to get the pressure, or you could, if you have a pump, you could put a pressure sensor and look at the load along with that. If you want speed, monitor the running speed. How do you get the running speed? You can use your current sensor, just where the motor is going on, so you have the running speed from that. And so the multi-parametric view of a machine is extremely important, and that's how we would model the data science going forward.
I would add to that, yeah, when you're thinking about moving forward with technology, think more than just that particular solution, right? So not only are we monitoring condition of our rotating equipment, but I'm still thinking of my controls guy sitting at 2 a.m. on a Saturday morning reading, you know, all of these things coming in. He's got BAS alarms, he's got air handler pressure alarms, he's got vibration alarms from his equipment. And you're eventually going to have to integrate that. So the two things, one is he's not trying to look at 25 different screens to figure out what's going on, and they don't have to necessarily diagnose the problem, they just need to be able to triage it, right? So if you see a drop in air pressure and you start seeing BAS alarms for the VFDs, and then you start seeing temperature or vibration going on all at the same time, you can almost say, okay, my motor's hosed, and triage that much faster with the more information you have. So think in long terms of how I'm going to use this information with the rest of the information that's coming in, and the particular people who are using and consuming that information, how that's going to help them perform their job both better and, more specifically, more efficiently, right? Decisions for them. Yeah.
In terms of return of investment, have you estimate how much are you reducing your failure rate as part of the implementation?
Almost all the ones I've priced where you just use the vibration monitoring with the alarm conditions, and you don't necessarily have consultants reading those on a regular basis, less than a 1-year ROI based on average failure rates is usually what I get. So the prices come way down. And so it's very cost competitive. I would encourage you to walk through the booth. Probably half of the people have some wireless solution. So think about what you need, and then look at the different vendors to see who has the best solution and fit for your long-term goals, right? He said I'm supposed to stop. I don't know if I can go over 5 minutes, right? You know, but I would think if you have a question, you got to answer it even if he doesn't get it on a recording, right? So she has a question.
You mentioned you have these implemented or installed on only a portfolio of the air handlers. So did you do any pre-analysis to select which ones to analyze first, or how did you select the initial, like the pilot project?
Yeah, so how do we select the ones to choose? Well, we were particularly looking to demonstrate the value of having this. And so where we were having problematic systems and we didn't really trust the infrequent sampling to keep them on track, we specifically focused on those. And then we wanted some diversity. That's why we picked an air compressor and a condenser pump and those kind of things to say, does it work on more than just this type of equipment? And so we really were trying, for the purpose of the pilot, to demonstrate, will this bring value to us, right? And it'd be similar for you. Yeah.
I know our guys that do a walk around routes find a lot of things that are not picked up in vibration. Visual inspection, hear things, smell things, all kinds of things. Did you see any loss in that when you went to a system that no longer had guys walking around actually being at the equipment with the data?
Yeah, it's a good question. We specifically focused on what value will vibration monitoring bring. So where are we currently doing vibration monitoring? And I think the middle picture on this slide right here gets to well, that's only one parameter, right? So you have pressure, you have temperature, you have ultrasound, right? So I'm assuming if you had ultrasound capable sensors, you could pick up air leaks and arcing and those kind of things, right? And if you had temperature sensitive or infrared capable imaging, you'd be able to pick up hot spots and those kind of things. So, we talk about, are these the eyes and ears of the engineer? Well, an engineer has a brain that has a lot more capacity than the typical electronic device today, right? So focus on where your challenges are. And again, we don't have to have guys going in where they're de-energizing equipment to do the vibration. That's a big advantage. And we get more frequent samples, and that was a big advantage, right? And then ability to make it available to a larger scale, larger audience. That was certainly important. And so this is back to, okay, where does that all fit in? The industrial age, right? In generation 1.0 was the industrial age, where they came up with steam generators and electric power. 2.0 was Henry Ford and the assembly line, right? 3.0 is robotics, where you can have robotics do a lot of this stuff. And then the fourth generation right now is where can I monitor the process steps with a cycle that gives me assurance of quality, right? I guess thanks to everyone. Yeah.